Hello, ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 2 course. Today we're going to be going over section 2.6, which is transforming linear functions. As we have learned before, linear functions are functions that form a line, and what we're going to look at is the different kind of transformations that you can do to a linear function. Basically, all transformations come to similar things. The first thing is, I'm not going to go with one, I'm just going to go with type. The first one is a horizontal shift. Now, a shift means that we pick it up and we move it. So a horizontal shift would be picking up the equation or the graph and moving it either to the left or to the right. For an example, let's say that we have a beautiful little graph here. And our beautiful little graph in green looks like this. It is a pretty simple equation of y is equal to x. And then what I can do is I can do a horizontal shift. I can take this graph and I take every point and I can shift it to the right 2 spaces. So now my new space would be, or my new graph would look something like this. The slope remains the same. The only difference is that I moved it to the right 2 spaces. This is called a horizontal shift. And if I'm looking at the general equation for transformations, the general equation for transformations is h of x, which is the new one, is equal to a number times f of x minus h, and then a plus k on the outside. So the minus h on the inside means that it's going to be a horizontal shift. The k on the outside means that we go up and down. And the a transformation controls scaling and orientation. So because this was a horizontal shift, and we were looking at the equation in green being y is equal to x, the horizontal shift occurs on the interior portion of our function. But our function is just plain old x. So the way we would write that would be y is equal to, open parentheses, x minus whatever our horizontal shift was. Since we are shifting to the right 2 spaces, we would say 2. Now, doing some fancy arithmetic, we can drop all the parentheses and we get y is equal to x minus 2. So there's a horizontal shift. The other kind of shift would be a vertical shift. And if horizontal means moving left-right, then obviously vertical must mean moving up and down. So let's take a look at the same graph, except that we are going to move it down 2 spaces. So we have our original graph in green, going up and to the right and down and to the left. And then we have a vertical shift. Now the vertical shift means that I take all of the points and move them down 2 spaces, so that it would look something like this. Notice how the slope doesn't change. It maintains the same method of movement, it just changes its starting point. So this would be a vertical shift. Now, again, if we're looking at our general equation for changes, this would be controlled by the plus k portion on the outside. So if I'm looking at my original being y is equal to x, then I would have a new one of y is equal to x, and then on the outside a plus, and then the direction that we're going. If we're going up, it's a positive. If we're going down, it's a negative. And if it's we tell how far we go. So by saying that we went down 2, we would have a negative 2. Now, doing some fancy arithmetic, we end up with x minus 2. Notice in this weird case that both the vertical and the horizontal shift ended up doing the same thing to our equation. It's weird. It happens, and it only happens with lines. When we start looking at more generalized equations and more generalized functions, this doesn't always occur. So please note that this is a freak accident. It isn't by design. All right, so let's go ahead and look at some more types of changes. The other two types of changes that we're going to look at today are reflections. Reflections. And what reflections do is they take your graph and they flip it. So if we were looking at our original equation again of y is equal to x, we would have that equation as a beautiful little line going right through the middle in green. And now if we reflect about the x-axis, so here's my x-axis, I'm going to reflect it, meaning that basically I put a mirror over it and I put everything equidistant from it. So if I look here, it's 1 down, which means that I go 1 up. This one's 2 down, so I go 2 up. This one's 3 down, so I go 3 up, and so forth and so on. Now if we look at this one, this is clearly y is equal to negative x if we were looking at our equations. So green is in y is equal to x. Red, which is our reflected one, is really y is equal to negative x. So for our general equation, if we're looking at, sorry about that, h of x is equal to a times f of x minus h plus k, the a portion, the multiplier, is what controls our reflections. So on this one, we are looking at our h of x being reflected over the x-axis would just be negative, and then whatever my original function was. For flipping over x-axis. Now what about flipping over the y-axis? Well, let's take a look at that one. Once again, I'm going to draw my beautiful little graph. And we're going to have green as our original and red as the transformation. Now here's my original green, and what I'm going to do is I'm going to reflect it over the y-axis. So I would look at how far away this piece is. Well, that's 1 away, so I'd move in the opposite direction. Really don't like the word opposite, but it fits here by the same distance. So this one's 2 away, so this one needs to be 2 away. This one's 3 away, so this one needs to be 3 away, etc., etc. And what do we end up with? Well, it got flipped via this direction. So it got reflected over the y-axis. When we're looking at our general equation, where we have h of x is equal to a times f of x minus h plus k, to flip over the x-axis, we negated the a. To flip over the y-axis, we actually negate the x on the inside. So in this case, we would see it more as a case of a times f of negative x minus h, and then plus k. Pardon me. The funny thing is that when it comes to lines, these reflections are almost indistinguishable a lot of the time. So we're going to have to be a little bit careful about them. All right, and for our next portion, this is about stretches and shrinks. Stretch and shrink. Not shrink, shrink. There we go. So this one is a little bit different in that we're actually changing the way our graph looks. In all of the others, we've either just reflected it or we have just moved it through the transformations of reflections and translations, respectively. On this one, however, it's going to be very different. These are going to be like Laffy Taffy. We are going to stretch and shrink them by using really amazing tools. Again, let's use the same parent graph. Because that parent graph is the parent graph of all lines, this is the Mac Daddy of line graphs. This is the Methuselah of line graphs, I guess you could say, or the Adam of line graphs, whatever you want to go with. I'm not sure what other stories that I could use for the first person ever kind of thing, but I think Adam's pretty widely accepted. So here we go. If I want to stretch and shrink, what I would do is I would multiply the distance by a factor. So for an example, if I wanted to do a multiplier of a factor of 2, I would start at this point right here. What is my y value at this point right here? It would be 0. Multiply it by a factor of 2. 0 times 2 is, well, it's still 0. And then over here, my y value was 1. What's 1 times 2? 2. And this one would be 2. 2 times 2 is 4. And this one's 3. 3 times 2 is 6. And then the same way, -1 becomes -2. -2 becomes -4. -3 becomes -6. And suddenly we have a new line. This one has been stretched by a factor of 2. So if we're looking at our original function, f of x minus h plus k, the a is what controls the stretch or the shrink. So in this case, I would be multiplying it by 2. So if my original function was y is equal to x, my new function would be y is equal to the stretch factor times my original function, or 2x. Shrinking is the same thing, only you're multiplying by a number less than 1. Let me rephrase that. By a number whose absolute value is less than 1. So I'm going to write that down as a note. Note. If the absolute value of a is greater than 1, then it stretches. And if the absolute value of a is less than 1, then it shrinks. Stretch and shrink. Stretch means that it gets taller by a factor. Shrink would mean that it would get shorter by a factor. All right, let's go ahead and move on to some examples. Example number 5,836,221. How would you change an equation so that it shifts to the left 3 spaces? Well, if we remember our original thing said the new equation is equal to a times the old equation of x minus h plus k. The h controlled the horizontal shift. The k controls the vertical shift. And the a controlled stretch. Well, I'm going to call that orientation and scaling. The sign controls the orientation, and the number controls the scaling. So if I was told, how would you change an equation so that it shifts to the left 3 spaces? Well, that would be a horizontal shift. So I would say subtract 3 from the x values. that would look something like this. Let's say that we are given y is equal to x. Now I want to subtract 3 from the x values. So what I would do for my new one is I have the same x, except that it's supposed to be a minus h inside of a set of parentheses. So I'm going to say a minus and then my horizontal shift. Because I am going to the left, that means that I subtract. So I put a negative 3 on the inside. Now we have x minus negative 3, which is really x plus 3. So a horizontal shift to the left 3 spaces would have the equation of x plus 3. Now I know what you're thinking. This is really confusing. Why is it that when I want to go to the left, I subtract, and when I want to go to the right, I add? Well, you can kind of think of it like being at an airport or being in an airplane, right? If you are inside of your hangar bay and you're in your little airplane, do you really want to go up, up, and away? And the answer to that question should be no, because if you go up, up, and away inside of your hangar bay, it's going to go crash, boom, and then people will be sad because there's a big fire over there. And he has 2 noses for some reason. There we go. So you don't want to go up, up, and away when you're on the inside. But when you're outside of the hangar bay, do you want to be able to go up, up, and away? Well, to be honest, that's what planes are made for, so I'm really hoping you would say yes. When we're outside, let's go up, up, and away. So when we're outside, we can move up and down. When we're inside, we can't move up and down, but we can move left to right. Now let's continue with this analogy. When we're inside of the hangar bay, let's say that we're giving our pilot directions, and our pilot is looking straight at us. So here's our little airplane, and the pilot's in there, and he's looking straight at us. So what we're going to do is we're going to pretend he's on the top, and we're going to say something like, raise your right hand. Now when we tell him to raise his right hand, he raises his right hand. What side is that? That's his left side. Well, from your point of view, it's the left side, but from his point of view, it's the right side because you're facing each other. So if he's raising his right hand, and it's on our left side, then what do you think would happen if we tell him to raise his left hand? Now, if we tell him to raise his left hand, he will raise his left hand, and it will be our right hand. So what's happening is we're getting reversed. We're getting mirror imaged. So when we're giving our pilot instructions, when we want them to go to our left, we say go to the right. And if we want him to go to our right, we tell him to go to the left. Same thing with math. Math is like giving instructions, and they're facing you. So when you want them to go to the left, you say go to the right. And if you want them to go to your right, you say go to your left. Alrighty then. I believe that is it for today's lesson. If you have any more questions, feel free to ask them. But in the meantime, it's time for homework. So here we go. Homework. Good old practice, the good stuff. The place where you learn the most because you are actually practicing what you were taught, rather than just sitting there passively with drool coming out onto your table. Ew. Alright, homework. This is, of course, section 2.6 for Algebra 2. And we are going to do numbers. 1 through 19 odd. And then I think that will be it. Wow, this is the easiest homework assignment I've ever given. Yep, section 2.6, numbers 1 through 19 odd. This will give you quite a lot of practice with this concept of shifting versus transformations versus translations versus reflections, etc., etc., etc. And since it's dealing with lines, lines are the exception to most rules. They're really weird. And when we move on to things like parabolas, things will make a lot more sense. But for now, just do 1 through 19 odd. And in the meantime, good luck and have fun.